Welcome to all of you in this session. The session regarding the fluid mechanics class, it will cover the most of the GATE syllabus and as well as the many competitive exam syllabus. Before going to the fluid mechanics subject, we want to give some introduction regarding the subject, the application oriented the fluid mechanics. That means where the application of the fluid mechanics is there. Which field we are enormous application is there, and those field we will talk about it now. So just we'll see directly come to the slide. Essential books regarding the fluid mechanics. Before starting the subject, I am sharing some short of books you can follow. These are the books. First one is the Introduction to the Fluid Mechanics and Fluid Machines by Professor S.K. Gautam Bishwas and Suman Chakraborty. Next one is the Fluid Mechanics books, another by Frank and White. Another for the problematic solution, you can get this books, that is the Fluid Mechanics and Hydraulic Machines by R.K. Bansal. These three are the popular books. Other than there are several books is there, you can use it. Mostly we are following here Mr. S.K. book in this session. So here in the application in the fluid mechanics, if we are talking about it, which field we are applying, there is an application. First of all, the automobile sector. In the automobile sector, there is a lot of fluid mechanics application is there. Next one is the industrial sector, just like the power plant sector. In the power plant sector, the flue gas system, air system, there are a lot of the fluid mechanics applications, superheated flow. So next, the fluid mechanics orientation is the spacecraft. So spacecraft means aircraft. We are talking rocket. Another is the watercraft, like the ship. Those all places there are enormous application of the fluid mechanics. Human body is the paradise of the fluid mechanics. The respiratory system and the cardiovascular system, all of the depends on the fluid mechanics. So other than this industrial application inside the human body also, so many application of the fluid mechanics is there. So this all about the application oriented, the fluid mechanics you can apply anywhere. And there are so many natural animate also there. The motion of the snake is also regarding the fluid mechanics. The swimming of a fish. This all the things is the natural fluid mechanics animate. Natural inanimate, there is like a cyclone, tornado, these are the natural inanimate. Raindrops falling, all are the natural inanimate. So there are several sectors, there's a lot of application of the fluid mechanics. Now, before going to the definition of the fluid, we just want to see the approach, which approach we should have taken here. Which approach we should have taken for the analysis of the fluid mechanics. So basically, fluid means, from our basic knowledge, we know the fluid is combination of the liquid. With the liquid substance, we can say it a fluid, as well as the gaseous system, we can say it a fluid. That means the intermolecular attraction force are not that much strong like a solid. So between two molecules, the attractive force is loosely bounded actually. Better to say, it's the loosely bounded. Attractive force, intermolecular attractive force is the slightly lesser than the solid. That is the classification of the fluid. So which approach for we should use in this fluid mechanics. Basically, in here, if you consider one system, that is a system, the system definition we have seen in the thermodynamics class, the system definition, the quantity over which we will concentrate, that is called the system. That means the mass is the constant. In case of the system, the mass is constant. So system approach is there. Another approach in the fluid is the control volume approach. Two approaches: system approach and control volume approach. System approach, the most of the equation is actually valid for the system. Those, that means Newton's laws of motions, all equations are for a set of system. That means in a system, we are taking one. Here you see, just this is a system. Some confined mass is there. Mass is a constant in the system, quantity. Whereas the control volume system, in the control volume approach, we are choosing one part, one volume. Over the volume, if there is any fluid flow, it is coming some fluid, some accumulation is taking place, and some fluid is going out. So fluid in, some accumulation, and fluid out. So enormous number of molecules is coming over the system, over the volume, and it's gone. So this approach is the control volume approach. We'll see the details in the kinematic chapter. It's we are known as the Eulerian approach. Another approach we could be able to say, we are taking one particle, we are tracing on the fluid particles. We are tracking one by one particles. It's a particle tracking approach. This approach is another name is a Lagrangian approach. So basically, this kind of the approach, either we are tracking the particle, that is the Lagrangian approach, each and every particle we are following up. Another, we take one volume. Over the volume, the enormous number of particles is coming. Some particles accumulated and some particles going from this volume. This is the control volume approach or Eulerian approach you are taking. So system is under control mass system, which is closely related to the Lagrangian relativity. Now, other than this, at which level we should consider in these cases? That means, if a similar way, if you take one confined space, over there is the, consider some gases there. These are the molecules of the gas. So you are considering here some gases there. Gas is present in this. Now each molecule, if you consider at the molecular level, each molecule can translate along x-axis, can translate along y-axis, it can translate along z-axis. So 3 translational degree of freedom is there. Similar way, this same molecule can rotate about x-axis, can rotate about y-axis, can rotate about z-axis. So same way, plus 3 rotational degree of freedom is there. So 3 translational degree of freedom plus 3 rotational degree of freedom. So total, a single molecule having 6 number of degree of freedom. So in this system, how many molecules are there? Let you take the number of molecules. N is a very large quantity. So total number of equation we have to solve here equation will come 6 into n. Each molecule having 6 degrees of freedom. So 6 equation will be there. If n number of molecules are there, total number of equations become just 6. It's a large quantity. This kind of approach is known as the molecular dynamics. Now, in the Avogadro hypothesis, we know at normal temperature and the pressure, that means at the NTP, normal temperature and the pressure, a gas molecules, a mole of the gas is, how many molecules can be there? There may be, n will become 6.023 nearly into 10 to the power 23. So 6.023 into 10 to the power 23 number of molecules in a mole of gas is present. Similar way, if you consider the same way at a NTP, that is nothing but 22.4 liter of gas, idle gas, we're considering. So per liter, can you imagine nearly around the 3 into 10 to the power 20, nearly 3 into 20 to the power 22 numbers of molecules per liter. So there are enormous number of molecules there. So molecular dynamics concept becomes this approach is not suitable for a larger system. If the system is very large system, we should not use the molecular dynamics. It can be valid if it's a very rarefied gas system we are considering in a 2-3 more molecules is there, maximum some numbers is there, then we can take this molecular dynamics concept. Other than the molecular dynamics, the approach is coming here is known as the microscopic approach. You see here, other than the molecular dynamics, one approach we are taking is the microscopic approach. What does it mean by the microscopic approach? We are taking, instead of each molecules, we are taking the statistical average of any properties. That means we are first considering the statistical average properties here, molecules. So some batch wise we are selecting. This batch having a statistical identical similarity. So stochastic measurement, it is like that. It is the microscopic approach. This approach is coming from the kinetic theory of the gas. It is also another tedious also. It is also tedious because this approach is also, if you want to get through this approach, it will be also very enormous. It is not also suitable for the large system. So instead of considering each molecules, instead of considering statistical average of the molecules, now your consideration will come as a bulk. That is macroscopic approach. That means the system, you are considering the system as a continuous system. Total system, whatever you are considering, that is a continuous system. What is the benefit of considering continuous system? Because you could be able to apply mathematical operation just like differentiation, integration. This mathematical operation you could be able to. If you are considering the system as a continuous system, that means one molecule, all molecules, no discrete in this nature. Bulk system we are considering it like a bulk. In such kind of the approach, some thing to be satisfied is continuum hypothesis. Continuum hypothesis is called. That means we are considering the system as a bulk system. That means it's a continuous system. This is called the continuum hypothesis. Because if you consider again, just you think about previously, just I'm telling, in 22.4 liter of gas, having 6.023 into 10 to the power 23 numbers of molecules. So it's a very huge molecules, huge number of molecules over the 22.4 liter of gases. So it can be better approach to consider as a continuous system. But a mathematical approach is also here. One number is given. This number is known as the Knudsen number. Knudsen number, it is defined by the what it is telling. It is telling about the molecular. This number is a non-dimensional number. Molecular mean free path divided by the characteristic strength. So molecular mean free path is considered as a lambda, characteristic strength. So Knudsen number is equal to lambda by. What does it mean by the molecular mean free path? That means in between two successive collision, a molecule's how much path statistically can be, statistical average path can be traveled is known as the molecular mean free path. So if molecules is collide with another molecules at here, after collision, it can travel a distance, and again the second collision with another molecule set. So this distance in between two collision, here one collision, here another collision. In between two collision, how much path, statistical average distance it can be able to travel is known as the molecular mean free path. Whereas the characteristics length means the length above which the characteristics of the fluid is going to change. Next, you will see in a pipe flow, if you consider a pipe flow, inside a pipe there is a fluid flow is there. So the which molecules are nearby to the pipe, it is velocity is tends to 0. That means here, whatever the molecules are near to the wall of the pipe, the velocity is 0. That is the no-slip boundary condition. The same way, the which molecules are the center of the pipe having a maximum velocity. So if you draw the velocity distribution, it will be like this. Velocity distribution. So it will be like this. Those molecules are nearby to the wall, those having no velocity, and which are at the center having more velocity. So if you go along the radius or diameter, you can see the characteristics of the fluid is changing. So in case of the pipe flow, the L is nothing but the D diameter. So if you go along the diameter, you see that characteristics of the fluid is changing. That is known as the characteristics length. The character of the fluid is changing is known as the characteristics length. Now this Knudsen number, what it implies to tell, if Knudsen number is less than 0.01, then the fluid system, we could be able to say that continuum system. Continuum flow, sorry. This type of the flow, if the Knudsen number is less than 0.01. If it is greater than 0.01 to up to 0.1, then the slipping starts. This kind of the flow is known as the slip flow. Same Knudsen number if it is in between 0.1 to 10. That is, the transition is now taking place. That means the continuous flow, continuum flow is now become transition is taking place. Already it started slipping at here. Now this kind of the flow is known as the transition. Transition flow. And above 10, if the Knudsen number is above 10, this kind of the flow is called the free molecular flow. That is the rarefied gas system. So the only one number, the Knudsen number, is defined our system. Which kind of the system we are in. So mostly we'll concentrate here regarding. So mostly we are concentrate here regarding the continuum flow in our analysis. So the total analysis about the course for is assigned for us is the Knudsen number less than 0.0. That means we are considering the fluid system or medium is a bulk medium. Or continuous medium. That's why we could be able to apply differentiation and integration both. Because differentiation and integration can be only applied this kind of the operator, mathematical operator, for a continuous system. In a discrete, we cannot apply differentiation or integration. So this is the approach we are talking about here. Now we'll see the property of the fluid. But to see the property of the fluid, before telling the property of the fluid, I want to give the introduction of the definition of the fluid is like the definition of the fluid. Just now I'm giving the definition. The fluid is such a, consider here, if you take one element, it is very exaggerated figure. The fluid element we are taking on small. So let you take this as the fluid element. Over the element, if you apply some force, this force is known as the shear force or shear stress. Stress into area is known as the shear force. So if you apply the shear force, it will undergoes for the continuous deformation. That means initially t is equal to 0 time, it was like this way. At t is equal to 1 second, it is like this way. At t is equal to 2 seconds, it is like this way. T is equal to 3 seconds, it will be like this. Similarly, this also is like this. Same manner. This also. So continuous angle change is occurring with the time. So fluid is such a substance which undergoes a continuous deformation under the influence of the shear stress. This shear force of stress, how negligible of its magnitude, it does not affect. The shear force magnitude may be very small, but still this element, this substance will undergo continuous deformation. So this kind of the fluid is known as this is the proper definition of the fluid. Fluid is such a substance which will undergo a continuous deformation under the influence of shear stress, you can say, maybe very infinitesimal small stress it is. Still, it will go for the continuous deformation. But if the fluid is at rest, there is no deformation. If fluid is at rest, there is no deformation. So as there is no deformation, means shear stress is also zero. No shear stress, no deformation. If fluid is at rest. But if fluid is at motion, there would be definitely some shear stress value and continuous deformation. So, if fluid is at rest, there is no shear stress, but there must be some normal stress. Will come in this. The property we will discuss, then we will discuss about it. There is no shear stress, but there obviously some stress would be there to establish the equilibrium. This force is known as the normal stresses. This stress. Now the fluid property we'll see one by one, the property of the fluid. Before telling to the is a prelude of the fluid properties. So it is determines of the characteristics of the fluid. Property definition, you know. What are the fluid properties? First property is pressure. What is pressure? In our definition, we know the pressure definition is the time average force per unit area is known as the pressure. More basic idea. Unit. To know about the pressure, we have to go a deep concept of the stress. Because previously we were talking about the normal stress and the shear stress. Stress is the two types of the stress, normal stress and the shear stress. In your strength of material subject, you might have seen. So over a body, if you consider this is the area, this area, normal stress is acting in this. And shear stress is along the area. Is normal to the area. The stress is known as the normal stress. It can be written as the sigma x, sigma y in this manner. And shear stress is the along the area, the shear stress. The stress is the two types. One is the normal, another is the shear stress. The first fluid property we'll talk about before. So some concept of the stress we'll see, then we'll come back to the pressure. Next fluid property we'll discuss here, that is the density. And specific gravity. Next one we'll discuss here is the viscosity. Bulk modulus. This all are the property of the fluid. Surface tension. One by one, this property we'll discuss in here. And last one, the vapor pressure. These all the properties we'll see